So this video we're looking at how light travels into other mediums. Previously we've seen light reflecting off other mediums, and now we want to look at what happens when light travels into it. So here is a glass block, and we're going to have a beam of light. We'll make it a red laser light just for fun, and that will travel into our glass block. Okay, so let's just label this. Oops, I need to let's get rid of that. I need to label it in a relatively easy to read. I'll change the colour again. There we go. This is glass, this is air, and that's our light that's coming in. Okay, so as you stare at it, all subsequent rays are going to be drawn small, but as you stare at it, you're not actually going to notice any visible difference when you're looking at it from, our perspective. A person's looking at glass and a light beam going in. However, what would be happening, let's just draw this as a wave, okay, is that this light ray is going in, it's got a particular initial velocity, and it's got a particular wavelength I, and it's got a particular frequency F. Okay, remember, and they are linked. I'm not sure if we've covered it yet, but I think we might have, but I'll mention it briefly. We've got the wave equation V equals F lambda, which links the speed of light, or the speed of the wave, because it doesn't just apply to light waves, it could be water waves as well. F is the frequency of the light, which is the speed at which the wave moves up and down, vibrating, if you like, as it travels. Trying to keep it relatively simple, that's not the main focus, so I won't labour that description. And the wavelength is the length of the wave from peak to peak before it starts repeating itself. So anyway, it hits this glass, and first thing that you would notice if you're able to measure it is that the velocity slows down, so it becomes a bit less. So I've drawn a shorter length vector, not by a great deal, but it's noticeable when you're taking measurements of these things. The other thing that you'd notice, if you could get down even deeper, is that the wavelength decreases. So you now have a new, shorter wavelength. Okay, and then when it comes back out again, the speed goes back to normal, and the wavelength also goes back to normal. I don't know if that's the same wavelength, but so the only thing that doesn't change is the frequency, which is cool, because that means it stays that same colour of light while it's inside there, because the light colour is associated to the frequency. Yeah, no, we'll just leave it at that. These are important factors because this is what causes the idea of refraction, which is, we're going to get into that in the next video, so I'm not going to get into detail, but if you had light coming in at an angle, it's going to bend as it comes through, so it's not going to follow the path that you would have thought it would. It actually bends in different ways, and as it's coming out again, the light will bend in a different way. But again, not getting into detail for there. The amount that it bends is related to this thing here, the refractive index. The refractive index is also a measure of, or can be a measure of, the changes in the speed and the changes in the wavelength. So the refractive index is a measure of what we call the optical density. Again, I'll talk about that in more detail in the next video too, but or in a different video. But diamond, for instance, has a greater optical density compared to glass. Glass has a greater optical density compared to water. Water has a greater optical density compared to air. And air in a vacuum, air is very much the same as a vacuum. It's so minuscule difference that we don't worry about it in our calculations this year. But anyway, if we were to work out an actual number, a physical value for the refractive index, we would look at the wavelength, excuse me, in this case it's I, the wavelength in air or a vacuum, over the wavelength in that particular medium of glass, which in this case is our F. So you might see notation of ones or air, A, IR, subscript air, or subscript glass or something like that. And this ratio happens to be the same as that velocity change. So the initial velocity over the final velocity. And you could actually flip this upside down on both sides and it would be the same. But what we also have, let's just move that a little bit so it's all on one page. Well, we also have that ratio there is equal to the refractive index of F, see this is upside down compared to the other two, over the refractive index of I. Okay, that's really important to note. The ratios of the speed and the ratios of the velocity are the inverse of the ratios of the refractive indexes, because glass will have a refractive index in glass, which in this case would be in F, and air also has a refractive index in air, which would be in I in our equation down here. Okay, so the greater the refractive index, the greater the bending of the rays at those interfaces, and the greater the change or decrease in velocity as it comes from air into it. Now, most refractive indexes are absolute, that is, they're made with reference to air or a vacuum. So that means you don't, how do we put this? The refractive index of diamond, for instance, is about 2.4, I think. So that would be in diamond, and that would be in diamond divided by the velocity of light in diamond divided by the velocity of light in air. Or did I get that round the wrong way? I did. I got that round the wrong way. My bad. Swap those two. So it's the velocity in air, which has to be larger because it slows down when it goes into the higher optical density, to diamond. See, we all make mistakes. You just got to make sure that you catch them at the right time. And because air is our kind of our fastest possible velocity light can be, that means that a refractive index, an absolute refractive index, is always going to be greater than 1. Okay, it's always going to be greater than 1. You can consider that a little bit more and follow through some of the examples a little bit further on, where we talk about refraction in more detail, and Snell's law, and total internal reflection, and a whole lot of cool stuff. There we go. Don't forget to come to the forum if you have any questions, or if you want to request a video that gets into particular detail that doesn't get covered otherwise. You're welcome to visit us on the contact page and send that through.